Hello everyone, welcome back to a new video. We have chapter 5, review and assess. Question 1, which band of the electromagnetic spectrum has A, the lowest frequency, B, the shortest frequency? As you remember, we had the electromagnetic spectrum, we had radio waves, and then we were all going down. We had 7 waves, and then we had gamma rays, which was the final one. Gamma rays. You have radio waves, you have microwaves, of course they should be in order. You have infrared, you have visible, ultraviolet, X-rays, and gamma rays. As we were going down, wavelength was decreasing. Okay, so radio waves, they had the highest wavelength, and gamma rays, they had the shortest wavelength. Okay, and we were saying that wavelength with frequency are inversely proportional. So if wavelength is high, means frequency is low. If wavelength is low, means frequency is high. So which band of the electromagnetic spectrum has the lowest frequency? Of course, radio waves. Radio waves, they have the highest frequency, the lowest frequency. Why? Because they have the highest wavelength. Which one has the shortest wavelength? Gamma rays. Gamma rays, they have the shortest wavelength and they have the highest frequency. Which one of the following electromagnetic waves has the highest frequency? Ultraviolet radiation, they have the highest among all these 4. They have the highest frequency. Radio waves, they have the lowest, and then you have blue light and then infrared. Okay. We have question 3. It says, why can light be used to measure distances accurately? Because the speed of light never changes. Okay, the speed of light is constant. It is equal to 3 times 10 to the power of 8 in a vacuum, and is equal to 2.99 times 10 to the power of 8 meter per second in air. Okay, so the speed of light does not change, and we can always measure the speed of light and use it to measure distances accurately. We have this diagram very simply. You have a wave front here, or a wave source here. It says, how would you represent this wave, a new wave front, in a ray approximation? So as you can see, this is a wave. It's going like this in this direction, and it's going from A to B. What's going to be the new wave front? It's going to be in a form of a circle, in a circular shape, like this, going from A to B. Okay, we have question 5. What is the relationship between actual brightness of a light source and its apparent brightness from where you see it? You remember we talked about inverse square law. Okay, we had brightness, okay, which was inversely proportional, or was following the inverse square law. Okay, so this is the relationship between the brightness and the actual color, the actual brightness of the light source. If you go, for example, if you double the distance between the light source and for example, the object, it's going to be following inverse square law. Let's say that you have a source of light here, and then this is a source of light, and then you have an object here. Okay, if you double that distance, okay, the brightness is going to decrease by what? By 1/4. Okay, this is the relationship between the actual brightness of a light source and its apparent brightness from where you see it. Question 6. Suppose an intelligent society capable of receiving and transmitting radio signals lives on a planet orbiting Procyon, a star 95 light years away. Okay, so we have a star which is 95 light years away. Away from Earth, of course. If a signal were sent toward Procyon in 1999, okay, what is the earliest year that Earth would expect to receive a return message? So first of all, this star is 95 light years away. So if you want to send a light ray, if you want to send a signal, it's going to take 95 light years. Okay, so 999 plus 95. Okay, this is what? This is the time that it takes for the light to receive, or for the persine, for the light to reach persine. This is going to be what? This is going to be 2094. Okay, this is the year that the aliens or the intelligent society are going to be receiving the signal. When it's going to come back, of course, it's going to take another 95 years, and this is going to be what? 2094, okay, plus 95, okay. Then this is going to be, this is going to be 2189. Okay, this is going to be the year which we will be, or which the signal is going to be returned from the persine, from the star. How fast do X-rays travel in a vacuum? All the electromagnetic spectrum is having the same speed, be it gamma rays, X-rays, ultraviolet, radio waves. They all have a speed of 3 times 10 to the power of 8 meter per second. Okay. Why do astronomers observing distant galaxies talk about looking backward in time? Because let me give you an example. The sun, our sun, it takes 8 minutes and approximately 20 seconds for its light to reach the Earth. Okay, so it's not immediately reaching us. Okay, it takes some time. Same thing is true for stars, but stars are farther away compared to the sun, so they might be billions and billions of light years away from us. Okay, as you see, we have an example here. They are 95 light years away from us. Okay, so the light that we see it now from the stars might be the sun, or the star might actually be dead. Okay, but it's just the light that we are receiving. Okay, it's just the light that now we are observing. Maybe in fact the star has died and it does not exist anymore. Okay, because we know that universe is really vast, and the stars are really far away from each other, some of them. Do the brightest stars that you see in the sky necessarily give off more light than dimmer stars? No, they might be basically closer to us. Okay, it doesn't necessarily mean that they are brighter. Okay, they might be closer to us. Question 10. The compound eyes of bees and other insects are highly sensitive to light in the ultraviolet portion of the spectrum, particularly with frequencies between 7.5 times 10 to the power 14 Hertz and 1 times 10 to the power 15 Hertz. So we have two frequencies. F1 is equal to 7.5 times 10 to the power 14 Hertz. And then you have F2, which is equal to 1 times 10 to the power of 15 Hertz. Okay? It says, to what wavelength do these frequencies correspond? So we need to find first lambda 1 is equal to what? Lambda 2 is equal to what? Okay? Remember, we had what? We had the equation for finding frequency. We had c, which is the speed of light, which was equal to frequency multiplied by lambda. So let's first find lambda 1. So lambda 1 is equal to what? Divide this by frequency 1, first frequency, and divide, cancel. So lambda is going to be c, which is the speed of light, divided by frequency. Speed of light is equal to 3 times 10 to the power of 8. And then we have what? We have f1. F1 is equal to what? It is equal to 7.5 times 10 to the power of 14. Okay, let's calculate this. We have 3 times 10 to the power of 8 divided by 7.5 times 10 to the power of 14. We have 4 times 10 to the power of minus 7 meters. Okay, or 400 nanometers. Okay, if you change it to nanometer. So this is the first wavelength. Okay, the second wavelength is going to be what? Again, C divided by F2 frequency, the second frequency. Lambda 2 is going to be what? 3 times 10 to the power of 8 divided by 1 times 10 to the power of what? Of, I think it's 14, yes, 15, sorry. Divided by 1 times 10 to the power of 15. Okay, so this is going to be what? This is going to be, let's calculate this. We have 3 times 10 to the power of minus 7 meter. So this is what, you can also change that to nanometer. It becomes 300 nanometers. Okay, we found lambda 1 and we found lambda 2. We have question 11. The brightest light detected from the star Antares has a frequency of about, this is wrong, this is 3 times 10 to the power of 14 hertz. What is the wavelength of this light? Wavelength is equal to C divided by frequency. Then we have 3 times 10 to the power of 8 divided by frequency, which is equal to 3 times 10 to the power of 14. Okay, make sure to calculate that and find the wavelength. What is the wavelength for an FM radio signal if the number on the dial reads 99.5? So we have frequency, which is equal to 99.5 megahertz. Don't forget to change that to hertz. This is going to be 99.5 times 10 to the power of 6 hertz. Okay, this is the frequency. Find the wavelength. Wavelength is equal to what? So wavelength is equal to C divided by frequency. 3 times 10 to the power of 8 divided by what? 99.5 times 10 to the power of 6. Let's calculate that. 3 times 10 to the power of 8 divided by 99.5 times 10 to the power of 6. Okay, we have 3.01 meter. Okay, this is the wavelength that we have for the FM radio. What is the wavelength of a radar signal that has a frequency of 33 hertz gigahertz? Okay, so we have 33 gigahertz. Okay, this is equal to it. Don't forget to change that to hertz. We have 33 times 10 to the power of 9 hertz. Okay, then find the wavelength. Wavelength is equal to what? It is equal to C divided by frequency. 3 times 10 to the power of 8 divided by what? By 33 times 10 to the power of 9. Let's calculate that. We have 3 times 10 to the power of 8 divided by 33 times 10 to the power of 9. So this is going to be equal to what? This is going to be equal to 9.09 times 10 to the power of minus 3 meters. Okay, this is the wavelength of the radar signal. We have question 14. For each of the objects listed below, identify whether light is reflected diffusely or specularly. A concrete driveway, it's a concrete, so this is diffuse reflection. An undisturbed pond, okay, this is undisturbed, it's calm, so this is going to be specular reflection. Okay, it's going to be regular reflection. We have polished silver tray. This is going to be also specular reflection because it's polished, it's a shiny surface. We have a sheet of paper. It's not, it's a rough surface, so this is going to be diffuse reflection. Okay, it's going to be reflected diffusely. A mercury column in a thermometer. It's smooth, so it's going to be a specular reflection. If you are stranded on an island, where would you align a mirror to use sunlight to signal a searching aircraft? You would place the mirror in a way that is going to reflect light to the aircraft, okay, by adjusting the angle of the mirror between the sun and the mirror, between the light rays of the sun and the mirror and the aircraft. If the sun is behind you, of course, the angle is going to change. If it's in front of you, of course, you are going to adjust it according to that. What are the characteristics of image in a flat mirror of a candle that is placed in front of it? So we studied all of this. The properties of the image formed by a flat mirror is that the image is virtual, it cannot be presented on a screen because it's virtual. They have the same size, the object and the image, the same distance too, and that's it. Okay, these are the properties of the image formed by a plane mirror. Is the reflection of a flat mirror due to the transmission of light from one medium into another? No, it's due to the reflection of the light rays, not transmission. Okay, light rays are not transmitted, they are reflected basically. Question 18, does the variation of the angle between two flat mirrors affect the number of images or of a source placed between them? Yes, we even have an equation for this. Number of images is equal to 360 degrees divided by the angle that we have. Okay, the angle between the two mirrors minus the minus 1, which is basically the object. Okay, so if you want to find the number of images formed by two images, we're going to have this equation. Does the variation of the angle between two flat mirrors affect the number of images? Of course, it's going to affect it. Okay, so if we have, for example, 90 degrees, okay, let's say theta is equal to 90 degrees. Let's find the number of images. We studied that 3 images are going to be formed. Let's see if that is true. Number of images is going to be 360 divided by 90 here minus 1. This is equal to 4. So n is equal to 4 minus 1. And we have 3 images. Okay, this is going to be what? This is going to be the number of images formed by two mirrors that are placed perpendicular to each other. If you are standing in a 2 meters away from a flat mirror, how far behind the mirror is your image? It's the same, okay? And magnification of the image, it's 1, okay? Because the magnification and the image size and the object size are the same. So if you stand 2 meters away from the mirror, so let's say this is a mirror, and you are standing here, 2 meters away from the mirror. What is the image distance? Of course, it's going to be 2 meters too. Same, okay? What is the distance between you and the image? It's 4 meters, okay? 2 and 2, that's going to be 4 meters. How would the shape of the reflected beam at a flat mirror when the incident beam is parallel? If it's parallel, it's going to be reflected in the same. If light ray is coming in a parallel way, it's going to be also reflected parallel to the mirror. Divergent, if the light rays are divergent, they're going to be spreading out. If they're convergent, they're going to be crossing at one point. We have, I think that's it, okay? We will solve the rest of the questions in the next video. See you in the next video.